Okay, now to part C, part 1, showing that if AB, so show that if I have a tuple AB inside this region, then QK will be the point probabilities in a Poisson distribution. And actually, we also want to find out specifically which parameters that Poisson distribution will have. So assume AB lies inside this region. And that means that we assume that A is equal to 0 and B is greater than 0. What do we then have about the QK? Well, then QK is equal to 0 plus B divided by K, QK minus 1, for K equal to 1, 2, 3, and so on and so on. So in particular, Q1 is equal to B multiplied by Q0. Q2 is equal to B divided by 2 multiplied by B multiplied by Q0, which is B squared over 2 Q0. Q3 will be equal to B over 3, and then B squared to Q0, and so on and so on. And QK will be equal to B to the K divided by K factorial multiplied by Q0. Or this is kind of the pattern that I see when I plug everything in. Um, I can prove this by induction, but I will not do this in the Poisson case. In the Poisson case, it's relatively simple. So I will wait for the induction proof until we do the binomial case where it's a bit harder. This is just to give you guys an idea of what's going on in general. So by plugging in qk minus 1, qk minus 2, and so on, I see that each qk can be expressed as b to the k divided by k factorial multiplied by q0. And this is nice because this implies that if I sum all of my qk, well, that is equal to b to the k divided by k factorial multiplied by q0 for k going from 1 to infinity. And then in the case where k is equal to 0, I just have q0. And I can actually also include that in my case here because b to the 0 is 1 and 0 factorial is 1. So I can just write the sum of qk's from 0 to infinity. I can just write them up as such. And this is equal to q0 multiplied by the sum of b to the k, k factorial. So that implies that that the sum of qk's can be written up as such. And just recall that the sum of qk's is the sum of point probabilities, which must be equal to 1. And this will then imply that q0 must be equal to whatever this sum is to the minus first, right? So what is this sum? Well, this is the Taylor series for the exponential function evaluated in B. So this is all in all e to the minus b. And since Q0 is given by e to the minus b, we can conclude that the probability distribution we're looking at is given by Q0 equals e to the minus b, and Qk equal to b to the k divided by k factorial multiplied by Q0, which is e to the minus b. And we recognize this very clearly as the Poisson distribution. So hence, the Qk are the point distributions, are the point probabilities in the Poisson distribution with specifically parameter b.